Hello everyone, my name is Belisario, and let's dig in. Ever wondered what really happens to your body when you start doing aerobic and anaerobic exercise regularly? Let's dive into the science of adaptation to aerobic and anaerobic training and how it transforms your body from the inside out. During a single bout of aerobic exercise, the human body precisely adjusts its cardiovascular and respiratory function to meet the energy and oxygen demands of actively contracting muscle. When with regular exercise training, they adapt in ways that allow the body to improve VO2 max and overall endurance performance. Regular aerobic exercise improves your heart and lungs' ability to deliver oxygen to your muscles, boosting endurance. Your body adapts to increased exercise demands, improving cardiovascular and respiratory efficiency. This enhanced efficiency allows for greater oxygen delivery to working muscles, improving performance and endurance. Improvements in endurance that accompany regular, daily, everyday, every other day, etc. aerobic training such as running, cycling, or swimming result from multiple adaptations to the training stimuli. Some adaptations occur within the muscles themselves, promoting more efficient utilization of oxygen and fuel substrates. Still, other important changes occur in the cardiovascular system, improving circulation to and within the muscles. Pulmonary adaptations, as will be noted later, occur to a lesser extent. Endurance is a term that refers to two separate but related concepts, muscular endurance and cardiorespiratory endurance. Each makes a unique contribution to athletic performance, and each differs in its importance to different athletes. For sprinters, endurance is a quality that allows them to sustain a high speed over the full distance of, for example, a 100 or 200 meter race. These components of fitness is termed muscular endurance, the ability of a single muscle or muscle group to maintain high intensity, repetitive or static constructions. This type of endurance is also exemplified by a weightlifter doing multiple repetitions, a boxer, or a wrestler. The exercise or activity can be rhythmic and repetitive in nature, such as multiple repetitions of the bench press for the weightlifter and jabbing for the boxer. Or the activity can be more static, such as a sustained muscle action when a wrestler attempts to pin an opponent. In either case, the resulting fatigue is confined to a specific muscle group, and the activity's duration is usually no more than 1 or 2 minutes. Muscular endurance is highly related to muscular strength and to anaerobic power development. While muscular endurance is specific to individual muscles or muscle groups, cardiorespiratory endurance relates to the ability to sustain prolonged dynamic whole-body exercise using large muscle groups. Cardiorespiratory endurance is related to the development of the cardiovascular and respiratory system's ability to maintain oxygen delivery to working muscles during prolonged exercise, as well as the muscle abilities to utilize energy aerobically. This is why the terms cardiorespiratory endurance and aerobic endurance are sometimes used synonymously. Cardiorespiratory endurance or aerobic endurance is the ability to sustain prolonged rhythmic exercise involving relatively large muscle groups. Studying the effects on endurance requires an objective, repeatable means of measuring an individual's cardiorespiratory endurance capacity. In that way, the exercise scientist, coach, or athlete can monitor improvements as physiological adaptations occur during the training program. Most exercise scientists regard VO2 max, sometimes called maximal aerobic power or maximal aerobic capacity, as the best objective laboratory measure of cardiorespiratory endurance. VO2 max is defined as the highest rate oxygen consumption attainable during maximal or exhaustive exercise. VO2 max, as defined by the Fick equation, is determined by the maximal cardiac output, delivery of oxygen and blood flow to working muscles and the maximal O2 difference of active muscles to extract and use the oxygen. As exercises intensity increases, oxygen consumption eventually either plateaus or decreases slightly even with further increases in workload, indicating that a rule maximal VO2 has been achieved. In addition to increasing maximal endurance capacity, endurance training also increases submaximal and endurance capacity, which is much more difficult to evaluate. A lower steady-state heart rate at the same submaximal exercise intensity is one physiological variable that can be used to objectively quantify the effect on training. Additionally, exercise scientists have used performance measures to quantify submaximal endurance capacity. For example, one test used to determine submaximal endurance capacity is the average peak absolute power output of a person can maintain over a fixed period of time on a cycle ergometer. For running, the average peak speed or velocity a person can maintain during a set of period of time would be a similar type of test. Generally, these tests last 30 minutes to an hour.
So there are multiple cardiovascular adaptations that occur in response to exercise training, such as heart size, stroke volume, heart rate, cardiovascular output together with blood flow. So it is important to remember that we can relate that to oxygen transport system, the ability to deliver sufficient oxygen to meet the needs of metabolically active tissues. The whole body oxygen consumption is determined by both the delivery of oxygen via blood flow, that is cardiac output, and the second is the amount of oxygen extracted by tissues, the AV, oxygen difference. So the ability to deliver cardiovascular and respiratory system, or the ability to deliver oxygen to our tissues, is defined by the Fick principle. The product of cardiac output and the AV O2 oxygen difference determines the rate at which oxygen is being consumed. So the formula is VO2 minus oxygen consumption is equal to stroke volume multiplied by heart rate and multiplied by EV oxygen difference. It is important to note that oxygen is important for our tissues to function, and our oxygen transport system plays an important role in meeting the demands that our body needs when exercising or in training that could involve adaptations of our cardiovascular system, including changes in heart size, stroke volume, heart rate, cardiac output, blood flow, together with blood pressure and blood volume. So let's begin with the heart size. So heart size on. So heart size as an adaptation to increased work demand, cardiac muscle mass and ventricular volume increases with training. So the left ventricle does most of the work to pump blood and thus undergoes greatest adaptation in response to endurance training. So kana mo ang left ventricle mo ang trabaho mostly. So the type of ventricular adaptation depend upon the type of exercise yapon nga gina perform. Just like for example, kanang during resistance training, the blood pressure or exercise can exceed up to 480 to 350 mmSg, and this demonstrates resistance that must be overcome by the left ventricle. So during endurance training, the left ventricle chamber size increases. So dako ang size chamber. Okay, mataas man ang demand sa oxygen, so madako gid siya. Taas ang kailangan man mag deliver og daghan mga oxygen. So you may wonder how we can measure our heart size, right? So there are a lot of instruments or kanang mga technology that could do this, but in measuring the heart size, we use kaning echocardiography. It involves techniques of ultrasound, which uses high intensity frequency sound waves that is diffracted to the chest wall to the heart. So when those sound waves have either contact with the heart, they rebound back to the sensor. So next adaptations is the stroke volume. So stroke volume is higher after an endurance training than it is before training, of course. So the graph shows changes in stroke volume during walking, jogging, and running, and increases it in velocities. So it's all about the changes in stroke of a subject who exercise at increasing intensities up to proximal intensities. So furthermore, in table 11.1, the wide range of stroke volume for any given cell within this table is largely attributed to differences in body and size. So, next one is kanina tawag na itong heart rate. So, heart rate in aerobic training has a major impact sa atong heart rate at rest. So, during submaximal exercises and during the post-exercises recovery period. So, let's begin with kanina tawag na so resting heart rate. So, ang resting heart rate decreases remarkably as a result of endurance training. Some studies have shown that a sedentary individual with an initial resting heart rate of 80 beats per minute can decrease its resting heart rate by approximately around 1 beats per minute with week na siya ng aerobic training, at least lagi for the few weeks. But after 10 weeks of moderate endurance training, resting heart rate can decrease from 80 to 70 beats per minute na lang. That is typically greater than high intensities ng mga exercises. So, next is kanina resting heart rate is typically lower by more than 10 beats per minute following by endurance training. So after endurance training, ang submaximal heart rate is likewise lower during exercises at the same absolute workload. So generally by around 10 to 20 beats per minute or more. So maximal heart rate generally does not change or decrease slightly with endurance training. But the graph shows the change of beat per minute during that progressive walking, jogging, and running as it increases the speed. So we have now the what do you call this one? Heart rate recovery. So heart rate recovery during exercises, heart rate must increase to increase cardiac output to meet the blood flow demand of active muscles. When the exercise bout is finished, heart rate does not instantly return to its resting level. Di siya mabalik dito sa bitaw. Like low, like mukay pa siya. It remains elevated for a while slowly until it's turned into its resting state. The time it takes for heart rate to return to its resting state is called the heart rate recovery period. So siya ginatawag na heart rate recovery period. And after endurance training, as shown in the graph, the heart rate returns to its resting level much more quickly after an exercise bout than it does before training. So, the next adaptation of the cardiovascular system is the cardiac output. So, we have looked at the effects of training on the two components of cardiac output. First we have is the stroke volume, ang pangalawa is heart rate. So while stroke volume increases, heart rate generally decreases at rest during exercise at a given absolute intensity, because the magnitude of these reciprocal changes is similar. Ang cardiac output at rest and during submaximal exercises at a given exercise intensity does not change much of the following endurance training. In fact, ang cardiac output can decrease slightly. This is likely the result of an increase in the AV or the oxygen difference na siya. Generally, cardiac output is mauni ang maghatag og oxygen required for any given intensity of effort to meet. Like, ang cardiac output during maximum exercise increases considerably and is largely responsible for the increase in the VO2 max or the supply or the consumption. of oxygen. Now, let's proceed to the blood flow. The blood flow in active muscles need considerably more oxygen and fuel substrates than inactive ones. Sila tong mas need kayo to meet the increased needs. Mas dagan nga blood ang dapat ma-deliver these muscles, like active muscles during exercise. So with endurance training, the cardiovascular system adapts to increase blood flow. Mag-adapt siya para increase ang blood flow to exercising muscles to meet their higher demand for oxygen and metabolic substrates. And there are 4 factors that will account for this enhanced blood flow to muscle. And these are the following. So the last one is the blood volume. Following endurance training is attributable to increase in both plasma volume and red blood cell volume. Like both changes facilitate the delivery of oxygen to active muscles. And what do you call this one? The increases in total blood volume and plasma volume occur with endurance training. Note that although the hematocrit, or the percentage of red blood cells, decreased from 44% to 42%, the total volume of red blood cells increased by 10%, as we can observe in the figure 11.7. So, let's now proceed to the next topic, which is all about the respiratory adaptations to training. To begin with, no matter how proficient the cardiovascular system is at supplying blood to exercising muscles, endurance would be hindered if the respiratory system were not able to bring in enough oxygen to fully oxygenate red blood cells. Respiratory system function does not usually limit the performance because the ventilation can be increased to a much greater extent than cardiovascular function. So, pulmonary ventilation. Pulmonary ventilation, siya ang what do you call this one? It decreases ventilation during submaximal exercise by as much as 20% to 30% at a given submaximal intensity. Maximal pulmonary ventilation is substantially increased from a rate of about 100 to 120 liter per minute in untrained sedentary individuals, about 130 to 150 liter per minute so nitaas siya. Pulmonary ventilation rates typically increases to about 180 liter per minute in highly trained athletes and can exceed 200 liter per minute in very large, highly trained endurance athletes. So, 2 factors can account for the increase in maximal pulmonary ventilation. So, following training, increased tidal volume and increased in respiratory frequency at maximal exercise. So we have another one, the pulmonary diffusion. Pulmonary diffusion or gas exchange occurring in the alveoli. So it can occur in the alveoli. It decreases at maximal exercise intensity, and this increases lung perfusion. So more blood is brought into the lungs for the gas exchange, and at the same time, ventilation increases that more air is brought into the lungs. So this means that more alveoli will be involved in pulmonary diffusion, and the pulmonary diffusion increases. Next is the arterial and venous oxygen difference. So, arterial, from the word itself, artery, and the venous, or the veins. So the AV oxygen difference increases with training, particularly at maximal exercise intensity. These increase results from a lower mixed venous oxygen content, and which means that the blood returning to the heart contains less oxygen than it would in untrained person. This reflects both greater oxygen extraction by active tissues and a more effective distribution of blood flow to active tissues. And that's what we all.
Metabolic adaptations to the training. Now that we have discussed training changes in both the cardiovascular and respiratory systems, as well as the skeletal muscle adaptation, we are ready to examine how these integrated adaptations are reflected by changes in three important physiological variables related to metabolism. First, lactate threshold, second, respiratory exchange ratio, and last, oxygen consumption. So in lactate threshold, it mentions traditional recommendations for improving aerobic power, continuous moderate to high intensity exercise, long, slow, low intensity exercise, or interval training. It highlights that HIT is a time efficient alternative. As you can see in the chart, the study involved young, healthy subjects performing 4 to 6 30-second sprints with 4-minute recovery periods, 3 minutes per week. This was compared to a group doing traditional continuous cycling for up to an hour, 5 days a week. So the result, both groups showed similar improvements in heart, blood vessels, and muscle. Improvement in exercise performance, majority by cycling time to exhaustion and time trials were comparable between groups, despite the HIT group having much lower time commitment. HIT appears to stimulate similar molecular signaling pathways as traditional endurance training, affecting skeletal muscle, remodeling carbohydrate, and for transport and oxidation. So next is respiratory exchange ratio, or RER. RER is a ratio of carbon dioxide released to oxygen consumed during metabolism, reflecting the composition of substrates used for energy. A lower RER indicates greater reliance on fats, while a higher RER indicates greater reliance on carbohydrates. After training, RER decreases at both absolute and relative submaximal exercises and intensities, indicating a shift towards greater utilization of free fatty acid instead of carbohydrates. Followed by resting and submaximal oxygen consumption. Resting VO2 remains unchanged following endurance training. The Heritage family study showed no increase in resting metabolic rate after 20 weeks of training. During submaximal exercise, VO2 is either unchanged or slightly reduced after training. The Heritage family found a 3.5% reduction in submaximized VO2 at a work rate of 50 watts, with a corresponding reduction to cardiac output. The decrease in VO2 during submaximal exercises could result from increased exercise economy. Last, maximal oxygen consumption, or VO2 max. VO2 max is the best indicator of cardiorespiratory endurance capacity and increases substantially in response to endurance training. A 50% to 20% increase is typical for a previously sedentary person training at 50% to 85% of their VO2 max 3 to 5 times per week, 20 to 60 minutes per day for 6.
And I am the reporter of Aerobic Power and Endurance Performance. So shall we start now? So, what limits aerobic power? So, aerobic power is mainly limited by the heart's capacity to pump blood, known as cardiac output, and by the muscle's ability to use oxygen efficiently through the mitochondria. If the heart cannot deliver enough oxygen, or if the muscle cannot properly use it, aerobic performance will decline. So, what limit endurance performance? So, what? Endurance performance is affected by several factors, which is depletion of energy stores, especially muscle glycogen. Next is overheating due to poor thermoregulation. Next is accumulation of lactate leading to muscle fatigue. Next is mental fatigue, which decreases focus and motivation. So, next slide. Long-term improvement with consistent endurance training. The heart becomes stronger, increasing cardiac output. New blood vessels form, enhancing oxygen delivery. Muscle cells produce more mitochondria, improving oxygen use. So these changes significantly boost aerobic power and endurance performance over time. So the summary of benefits is greater oxygen delivery to muscles, longer lasting endurance. Lastly is better resistance to fatigue and heat stroke. So that's all my part.
Factors affecting an individual response to aerobic training. So, an individual response to aerobic training can be vary significantly due to their several physiological, genetic, and environmental factors. So, the first that can affect our performance during an aerobic training is our genetics. It plays a major role in determining baseline aerobic capacity like maximum oxygen intake, and it influences much an individual can improve with their training. And genetic differences in muscle fiber types like mitochondrial density and enzyme activity can affect our performance. And second is our age. Most younger individuals tend to have a higher capacity rather than adult. And maximum oxygen intake and overall cardiovascular efficiency decline with age, although training can slow this decline. So the third is our sex. So most males generally have a higher max oxygen intake rather than women because they have a larger heart size, higher hemoglobin levels, and greater muscle mass. But also, females can still show significant improvement relative to their baseline levels. And the fourth is our nutritional status. Adequate intake and macronutrients and micronutrients supports training and recovery. Like carbohydrate availability is particularly important for endurance performance. So, next is health status chronic conditions. For example, cardiovascular disease, diabetes, and respiratory issues. So, it can affect both baseline and capacity and responsiveness to our aerobic training.
Changes in anaerobic power and anaerobic capacity. First, let's define these two terms. First is the anaerobic power. Anaerobic power refers to the ability to generate rapid, high-intensity efforts. Anaerobic training increases anaerobic power by enhancing neuromuscular function and muscle fiber recruitment. On the other side, anaerobic capacity refers to the ability to sustain high-intensity efforts over time. Anaerobic training increases anaerobic capacity by enhancing energy production and buffering capacity. Examples are sprinters, weightlifters, and gymnasts. All require high anaerobic power and capacity to perform their sports. Anaerobic training increases anaerobic power by first is enhancing neuromuscular function. Anaerobic training improves the communication between nerves and muscles, allowing for more efficient muscle contractions. Second is increasing muscle fiber recruitment. Anaerobic training recruits more fast-twitch muscle fibers, which are responsible for generating rapid and powerful contractions. On the other hand, anaerobic training increases anaerobic capacity by first enhancing energy production. Anaerobic training increases the production of energy-rich phosphates such as ATP and phosphocreatine. Second, improving and buffering capacity. Anaerobic training enhances the body's ability to buffer lactic acid and other metabolic byproducts, delaying fatigue. Measuring anaerobic power isn't as straightforward as measuring aerobic power. While VO2 max is widely accepted as the gold standard for aerobic power, there's no single test that accurately captures anaerobic power. Researchers have relied on three key tests: first is the Wingate anaerobic test. The second is critical power test. And the third one is the maximal accumulated oxygen deficit test. The Wingate test is the most widely used, where you pedal a stationary bike at a maximum speed of 30 seconds against high resistance. This test measures peak power output and mean power output, giving insights to anaerobic power and capacity. When you take the Wingate test, the braking force is tailored to your weight, sex, age, and fitness level. Your power output is tracked throughout the 30 seconds, and your peak power output is the highest mechanical power you achieve, usually within the first 5 to 10 seconds. This is considered as a measure of your anaerobic power. Your mean power output and total work done over the 30 seconds give an idea of your anaerobic capacity. Anaerobic training, like sprinting on a track or stationary bike, can increase both peak anaerobic power and anaerobic capacity. Studies have shown varying results, with some reporting minimal gains and others showing improvements to up to 25%. By understanding how anaerobic power and capacity work, you can tailor your training to achieve your goals.
Adaptation and muscles with aerobic training. Aerobic training refers to exercises that do not rely primarily on oxygen for energy production. These activities, such as sprinting, heavy lifting, and high-intensity interval training, or HIIT, involve short bursts of high-intensity effort. Over time, muscles undergo specific adaptations to improve performance during aerobic activities. Muscle adaptation. Muscle fiber changes. Aerobic training leads to hypertrophy or growth of fast-twitch type 2 muscle fibers. These fibers are responsible for generating quick, powerful movement but fatigue quickly. With training, they become thicker and stronger, increasing overall muscle size and force production. Increase enzyme activity. The body enhances its ability to produce energy without oxygen by increasing the ability of aerobic enzymes such as creatine kinase and phosphoproteokinase. These enzymes help speed up energy production through the ATP-PC system and glycolysis. Greater energy store. Muscles adapt by storing more phosphocreatine, ATP, and glycogen. This larger energy reserve allow for longer or more intense bouts of aerobic effort before fatigue set in. Improve buffering capacity. Aerobic exercise increases the muscle's ability to handle the accumulation of hydrogen ions, which cause the burning sensation during intense exercise. Improve buffering capacity delays fatigue and allow athletes to perform at high intensities for longer. Connective tissue strength. Tendons, ligaments, and the surrounding fascia become stronger and more resilient with aerobic training. This helps protect muscles from injury during explosive movements and heavy loads. Neural adaptation. Along with muscular changes, the nervous system becomes more efficient at recruitment muscle fibers, improving strength, coordination, and reaction time.